Video, we'll be discussing about Physics Paper 2, 8th level structured question, 2019 May-June, variant is 21, and the subject code is 9702. Point part A, define velocity. So velocity is change in displacement per unit time. Velocity is change in displacement per unit time. The speed v of a sound wave through a gas of pressure P, density ρ is given by the equation. So speed v is equal to kp by rho, where p is the pressure, rho is the density, where k is a constant and has no unit. So k is a constant with no units. An experiment is performed to determine the value of k. The data from the experiment are shown in figure 1.1. So we have given the quantity, their values, and the uncertainty. And you have to remember that the uncertainty that we have given is percentage uncertainty. So we have given the value of percentage uncertainty and not the value of absolute uncertainty. That is, we have given the value of percentage uncertainty. Use the data from figure 1.1 to calculate k. Now here we have to use this data from figure 1.1 to calculate k, and we have also given the equation. So v is equal to kp by rho to the power 1 by 2. So as there is a power of 1 by 2, so we can cancel this by multiplying 2 on both sides. So 1 by 2 and 2 cancels. So v square is equal to kp by rho. So k is equal to v square rho by p. V square rho by p. So we have to square v into rho by p. So v square, that is 3.3 into 10 to the power 2 square into rho, that is 1.29 by p, that is 9.9 into 10 to the power 4. So 9.9 into 10 to the power 4. So after calculating, we get a value that is 1.419. That is approximately 1.422 significant figures. Then use your answer from B1 in B1 and the data from figure 1.1 to determine the value of k with its absolute uncertainty to approximate number of significant figures. So with its approximate uncertainty, we need to find the value of k and its uncertainty to approximate number of significant figures. And we need to find absolute uncertainty. But here in figure 1.1, we have given the value of percentage uncertainty. So percentage uncertainty. So we have given the value of percentage uncertainty and we need to find the value of k and its absolute uncertainty. So we already know the value of k, that is 1.4. So percentage uncertainty in k is equal to, so for uncertainty, since we have given the value of percentage uncertainty, so we need to calculate our answer in terms of percentage uncertainty. So this is our equation, that is percentage uncertainty in k is equal to, since it is v square, so 2 into percentage uncertainty in v plus percentage uncertainty in rho plus percentage uncertainty in rho plus percentage uncertainty in p. That is 2 into percentage uncertainty in v plus percentage uncertainty in rho plus percentage uncertainty in p. So what is the percentage uncertainty in k? 2 into percentage uncertainty in v, that is 3, plus percentage uncertainty in rho, that is 4, plus percentage uncertainty in p, that is 2. Though p is divided, but we need to add the uncertainty. Whether it is divided or multiplied, we need to add the uncertainty. So the percentage uncertainty in k is 12%. Now percentage uncertainty is equal to absolute uncertainty by the true value into 100%. That means 12% is the percentage uncertainty, and we need to find the approximate change in the value of k divided by the value of k, that is 1.4 into 100%. So what is the approximate change in k, that or the approximate uncertainty or the absolute uncertainty? So what is the value of absolute uncertainty in k? So we get a value that is 0.168. So 0.168, and you have to remember that whenever we need to write the value of uncertainty, we need to give the answer to one significant figure. So we can convert this to one significant figure, that is approximately 0.2. Since there is a 6, so 1 is added to this one, so 0.2, that is one significant figure. So approximate number of significant figure, that is when we write the uncertainty, we have to give our answer always to 1SF or one significant figure. And the value of k, that is 1.4, is to two significant figures. So 1.4 plus minus 0.2. And you have to remember that whenever we need to write the uncertainty, we need to give our answer to one significant. Question number 2. A block X slides along a horizontal frictionless surface towards a stationary block Y as illustrated in figure 2.1. So block X moves towards block Y and the block Y is stationary and the surface is a frictionless surface. There is no resistive force acting on block X as it moves towards block Y. At time t is equal to 0, block X has momentum given. So we have given the value of momentum for block X. And what is momentum? So we know that momentum is equal to mass into velocity. Momentum is equal to mass into velocity. A short time later, the blocks collide and then separate. The variation with time for the momentum of block Y is shown in figure 2.2. So for block Y, we have given the momentum against time graph for block Y. So initially, block Y is at rest. So the momentum is 0 and as the two blocks collide, so there is a change in momentum. As the two blocks collide, so a force must act. So as collision occurs, force must act. And we know that resultant force is equal to change in momentum by change in time. So since force acts, so there is a change in momentum. So here we can say that since the force is acting, so there is a change in momentum, and due to this change in momentum, there is a force acting due to collision. And after the collision, there is no force acting. Since after the collision there is no forces acting, so the resultant force becomes 0. So the change in momentum 0 and the momentum again reaches a constant value. Then define linear momentum. So linear momentum or momentum is the product of mass into velocity. So momentum is the product of mass into velocity. Then use figure 2.2 to determine the time interval over which the blocks are in contact with each other. From figure 2.2, we need to determine the time interval for which the blocks are in contact with each other. So initially, y is stationary. Since we have given that y is stationary and we know that momentum is equal to mass into velocity, so as y is stationary, so its velocity is 0. Since the velocity is 0, so the momentum of y is 0. So initially y is stationary, so the momentum is 0. And as collision occurs between x and y, there is a change in momentum. So as collision occurs, there is a change in momentum. So there must be a change in momentum. And so as collision occurs, there is a change in momentum. So here we can see that there is a change in momentum, or as collision occurs, the force acts on the objects. So the resultant force acts on the object, and we know that resultant force is equal to change in momentum by change in time. So as collision occurs, there must be some resultant force. So since there is some resultant force, so there is a change in momentum. So we need to find that the time at which the blocks are in contact. That means since the blocks are in contact, so there must be some force acting when they are in contact. So since force is acting, so there is a change in momentum. Force is acting, there is a change in momentum. So there is a change in momentum from 60 time t is equal to 60 millisecond to time t is equal to 100 millisecond. So 60 to 100 millisecond. So what is the difference in time between the time interval? So that is 40 millisecond. So for 40 millisecond, the blocks are in contact with each other. So for 40 millisecond, the blocks are in contact with each other. So the force is acting, and since force is acting, so there is a change in momentum. And here we can see that there is a change in momentum. So the force is acting, therefore the blocks are in contact for 60 to 100 seconds. That is a time interval of 40 seconds, 40 milliseconds. So 40 milliseconds. Then describe without calculation the magnitude of acceleration of block Y from time t is equal to 80 millisecond to time t is equal to 100 millisecond. So we don't need to give a calculated value or the numbers such as 8, 10. Instead, we need to just state whether it is constant, increases or decreases. So what is the magnitude of acceleration? So from 80 to 100 millisecond. So from 80 to 100 millisecond, here we can see that for block Y, the momentum, there is a change in momentum. So we know that resultant force is equal to change in momentum by change in time. Also we know that resultant force is equal to mass into acceleration. So from 80 to 100 millisecond, here we can see that there is a change in momentum. Since there is a change in momentum, so there must be some resultant force. And since there is a resultant force, so there must be some acceleration. So acceleration has some value. And here we can see that the gradient of the momentum time graph is the resultant force. So for example, the gradient of displacement time graph is velocity. Similar to that, the gradient of momentum time graph is the resultant force. So gradient of momentum time graph is the resultant force. So here we can see that the gradient is constant. Since the gradient is constant, so the resultant force is constant. And since the resultant force is constant, while the mass is same, so the acceleration is also constant. So for momentum time graph, here we can see that the gradient is constant. Since the gradient is constant, so the gradient of the momentum time graph is the resultant force. So resultant force is constant. And since resultant force is constant and the mass is same, so the acceleration is also constant. So what is the acceleration? Acceleration is constant. And what happens to the acceleration from 100 to 120 millisecond? What is the acceleration from 100 to 120 millisecond? So from 100 to 120 milliseconds, so 100 to 120 millisecond. So here the gradient of the momentum time graph is 0. So we know that resultant force is equal to change in momentum by change in time. And we also know that resultant force is equal to mass into acceleration. So here we can see that the gradient of momentum time graph is the resultant force. So here we can see that the gradient is a horizontal line. And since the gradient is a horizontal line, or the gradient is 0. Since gradient is 0, so the resultant force is also 0. So the resultant force is 0. And since the resultant force is 0, mass is constant. So acceleration is also 0. Resultant force is 0. Therefore acceleration is also 0. So what happens to the acceleration? The acceleration is 0. Use figure 2.2 to determine the magnitude of the force exerted by block X on block Y. So we can calculate the force. That is, force is equal to change in momentum by change in time, since we have given the momentum time graph. And we need to determine the magnitude of the force exerted. So magnitude of the force exerted. So first of all, what is the magnitude of the force exerted? So for magnitude of the force, that is the force exerted. So the force is exerted when they are in contact with each other. For example, two objects that are far apart are not in contact, so no force is exerted on them. Otherwise, they are electric or magnetic charge. But here we can see that for these two objects, when they are in contact with each other, then the force is exerted. And when the objects are in contact with each other, so the objects are in contact with each other from 60 to 100 millisecond. So at this point, the objects are in contact with each other. So at this time interval, the objects are in contact with each other. So here the force is exerted. So what is the force? So force is equal to change in momentum by change in time. So change in momentum, what is the final momentum? Final momentum is 0.50. So resultant force is equal to change in momentum by change in time, and the final momentum is 0.50 minus the initial momentum, that is 0, by change in time. So 60 minus 100, 100 minus 60, that is 40 millisecond, and milli means 10 to the power minus 3 seconds. So 0.50 by 14 10 to the power minus 3. 0.50 by 14 10 to the power minus 3. So the force that we get is 12.5 or approximately 13 Newton. So we must give our answer to significant figure, that is 13 Newton. Then on figure 2.2, sketch the variation of momentum of block X with time from time t is equal to 0 to time t is equal to 160 milliseconds. It would be the momentum time graph for X from 0 to 160 millisecond. So for object X, I have drawn the momentum time graph for object X. That is for object X. So here for the momentum time graph, so for object X, I've drawn the momentum time graph. And so for X, we know that initially it has a momentum of 0.40 kg meter per second. So initially before the collision, so collision occurs at this time. So before collision, it has a momentum of 0.40. So initially it has a momentum of 0.40 before collision. And we know that momentum is always conserved. Momentum is always conserved. And since momentum is always conserved, so the momentum before collision must be equal to the momentum after collision. So the momentum before collision is equal to momentum after collision, as momentum is conserved. So what is the momentum before collision? So initially x has a momentum of 0.40. So 0.40, and y is at rest, so its momentum is 0. So here we can see that y is rest, so its momentum is 0, is equal to the final momentum or the momentum after collision. So momentum before collision is equal to momentum after collision. So what is the momentum after collision? So we know the momentum after collision for y, that is 0.50. So for y it is 0.50, but what is the momentum for x? So we consider this as momentum x, that is px. So what is the momentum of x? Momentum of x is equal to 0.40 minus 0.50. So we get a value that is negative 0.10. So it is negative 0.10. So the final momentum for x, that is after collision, is negative 0.10. So negative 0.10. So if we join the two lines, then this is the change in momentum, and initially this momentum, and finally this momentum. So again, if we just recall, then momentum is always conserved. And since momentum is conserved, so momentum before collision must equal to momentum after collision. And before collision, we know that the momentum of x, that is 0.40, y is at rest, so momentum is 0. So momentum is 0. And after the collision, so after the collision, we have given the momentum of y. So what we have given the momentum of y as 0.50. So 0.50. So what is the momentum of x after collision? So we consider this as px, as the momentum of x after collision. So what is the value of px? So px is equal to 0.40 minus 0.50, that is negative 0.10. So this is the final momentum for block x. So block x, the final momentum is negative 0.10. And if we join the two lines, then this is the graph for x. There is a momentum time graph for x.
For question number 3, the variation in extension x of the force F acting on the spring is shown in figure 3.1. So this is the force against extension graph. So the spring of unstretched length 0.40 has one end attached to the fixed point as shown in figure 3.2. So the unstretched length spring has initial length, that is LO, as 0.40. Then a block of weight 2.5 Newton is attached to the spring. The block is then released and begins to move downwards. So now the block of weight 2.5 Newton is attached to the spring, and now the spring moves downward, or it extends, and this is the final length. At one instant, as the block is continuing to move downwards, the spring has a length of 0.72 meter as shown in figure 3.3. So 0.72 meter as the final length. Assume that the air resistance and the mass of the spring are both negligible. So air resistance and the mass of the spring is negligible. Now for part A, for the change in the length of the spring from 0.40 to 0.72, use figure 3.1 to show that the increase in elastic potential energy of the spring is 0.64 joules. 0.64 joules. So what is elastic potential energy? So we know that elastic potential energy is equal to half Fx or half kx square, where k is the spring constant, x is the extension, extension is final length minus initial length. So x is the extension and F is the force. So we need to use figure 3.1. So this is figure 3.2 and 3.3. And we need to use figure 3.1 to find the force and the extension. So we need to use figure 3.1 to calculate the increase in elastic potential energy. So from figure 3.1 we so here it is mentioned that increase in length from 0.40 to 0.72 meter. So what is the increase in length of the extension? So the extension is 0.72 minus 0.40. So the extension that we get is 0.32 meter. It is 0.32 meter. And here it, since for figure 3.1 it is a force against extension graph. So we need to get our extension in order to calculate the value of force. So the extension is 0.32, and for 0.32 extension the force is 4 Newton. So the force that we get is 4 Newton for an extension of 0.32 meter. This is x, that is the extension, final length minus initial length. So elastic potential energy would be half Fx, that is half 4 into 0.72 minus 0.40, that means 0.32. So the elastic potential energy that we get is 0.64 joules to two significant figures as shown. You have to mention shown. Now we need to use figure 3.1, and if we, let's suppose we use 3.2 or 3.3, and instead of just and if we just ignore this, then we can see that the weight is 2.5 Newton. That means the force would be 2.5 Newton. 2.5 Newton. 2.5 Newton. So since we can see that the weight is 2.5 Newton, so we can consider the force as 2.5 Newton. But this would be wrong because we need to use figure 3.1. So from figure 3.1, we get the force as 4 Newton. So you have to remember that what is mentioned in the question, that which figure do you need to use. Calculate the decrease in gravitational potential energy of the block of weight 2.5 Newton. So now we can consider the weight of the force as 2.5 Newton. So the gravitational potential energy, that is GPE, is equal to mass into gravitational field strength into height. And so we have given the value of weight. For the weight that is 2.5 Newton, and we know that weight is equal to mass into gravitational field strength. So mass into gravitational field strength is equal to 2.5 Newton. So mass into gravitational field strength is equal to 2.5 Newton. And what is the height or the increasing height? So calculate the decreasing gravitational potential energy. So what is the decreasing height? So here we can see that initially, let's suppose this is the base level, and from this base level the initial height is, so this is not the height, the initial height is, okay, instead of considering this, what is the decreasing height? Initially our point is at this point, now it is at this point. So from this point to this point, what is the change in height? So the changing height, that is 0.72 minus 0.40, we get a change in height, that is 0.32 meter. So this difference in height is 0.32 meter. 0.32 meter, that is 0.72 minus 0.40 is this difference in height or the decreasing height. Since the height decreases, so the gravitational potential energy also decreases. So the decreasing height is 0.32 meter. So the height is 0.32 meter. After multiplying, we get a decreasing gravitational potential energy as 0.8 to one significant figure. This answer is to one significant figure, but for physics, we need to give maximum amount of answers. That means almost all the answers to two significant figures. So we need to convert this to two significant figure, that is approximately 0.80 to two significant figure, that is 1, 2. And if you write this answer, then this might be wrong. So it is better to write our answer as two significant figure as given. So use your information in A1 and your answer in A2 to determine for the instant when the length of the spring is 0.72 meter, the kinetic energy of the block. So from A1 and A2, so we need to use both the answers. So from A1, there is an increase in elastic potential energy, and from A2, decrease in gravitational potential energy. So initially, at the topmost point, because the base of the spring is at this point, so we consider this point as the topmost point, and now this is the final point. So if we consider this point, since it is at the greatest height or at the topmost height, so initially we have gravitational potential energy, GPE. So initially we have gravitational potential energy and no other energy, since it is an unstretched spring, and after the spring has extends, it has obviously elastic potential energy, that is elastic potential energy after the spring extends, plus kinetic energy, that is EK. So initially we have gravitational potential energy, and this gravitational potential energy is changing to elastic potential energy plus kinetic energy. So initially we have gravitational potential energy, that is gravitational potential energy, and this gravitational potential energy is converted to kinetic energy and elastic potential energy, and elastic potential energy due to the extension of the spring. So the decrease in gravitational potential energy, that is 0.80, that is 0.80 is equal to the increasing kinetic energy, and we need to find the kinetic energy or the increasing kinetic energy, that is del EK plus the increasing elastic potential energy, that is 0.64. So increasing kinetic energy is equal to 0.80 minus 0.64, that is 0.16 to two significant figures. So this is the increasing kinetic energy. Then the speed of the block. So now we need to convert the speed of the block, and we can calculate this from kinetic energy. So kinetic energy, we know that kinetic energy is equal to half mv square. So we know the value of kinetic energy. We know that it is half. And what is the mass? So initially, we know that you have to remember that we need to use A1 and A2. So from A1 or A2, we know that the weight is 2.5 Newton. So the weight is 2.5 Newton. So what is the mass? Mass into gravitational field strength is equal to 2.5 Newton. This is 2.5. So mass is equal to 2.5 by gravitational field strength, that is 9.81. So 2.5 by 9.81 into V square. And we need to find this V or the speed. So after calculating, we get the speed as 1.1 meter per second. That is two significant figures. Number 4. Question number 4 is related to electric field. So this is not in our syllabus, but there are two basic questions that you can solve, and the rest of the answers are related to electric field, so they are not in our syllabus right now. So for question number 4 part A, since these two questions are the basic question, so we can solve this, that is for part A and part 2. So we have given the radius and the density. Now show that the mass. So we need to find the value of mass. So what would be the mass? So by using the radius, we can calculate the volume. That is, volume is equal to 4 by 3 pi r cube. That is 4 by 3 pi and radius cube. So we get the value of volume. Now density is equal to mass by volume. So mass is equal to density into volume. So density into volume. So we know the density that is given and the volume that we have calculated. So we get this value of mass as shown to the given. Now oil droplet is charged. Explain why it is impossible. For the magnitude of the charge to be 8 into 10 to the power minus 20. So why this magnitude of charge is impossible? Because for charge, we know that the elementary charge is 1.6 into 10 to the power minus 19 coulomb. If you don't know, then it is not necessary for you. But if you know, then we can solve this. That the elementary charge is 1.6 into 10 to the power minus 19 coulomb. And for this charge to be a valid charge, it must be a multiple of this charge. Since this is the elementary charge or the charge of one electron, elementary charge or the charge of one electron. So for this charge to be a valid charge, it must have to be a multiple. So it have to be a multiple of the elementary charge. So if we divide this number by the elementary charge, then we would get a fraction or a decimal number. Therefore, it is not a multiple of this charge. Therefore, it is not a valid charge, or it is an impossible magnitude of charge. So the minimum charge on the oil droplet is 1.6 into 10 to the power minus 19 coulomb. And the rest of the answers are related to electric field. So this is not in our syllabus. Part A. A loudspeaker oscillates with frequency f to produce sound waves of wavelength lambda. So we have given the value of frequency and the wavelength of the sound. The loudspeaker makes n number of oscillations in time. So n number of oscillations in time t. So we know that frequency is equal to number of oscillations per unit time. So number of oscillations per unit time. So n number of oscillations and time. So state expressions in terms of some or all the symbols f, lambda and n for the distance moved by a wavefront in the time t. So that distance moved by a wavefront. So basically, we need to just calculate the distance moved. So what is the distance? So distance is the number of waves produced and the lambda. that is lambda is the wavelength for one wave. So the wavelength for one wave into number of waves, that is n. So n is the number of oscillations. So the loudspeaker makes this much oscillations. So this much waves must be produced, and so this much waves must be produced, and each wave has a length of lambda. So the total length or the total distance is n lambda. That is number of waves into wavelength is the total distance mode. So the time t. So time t. So we know that frequency is equal to number of oscillations by time. So time is equal to n by f. That is n by f. And also frequency is 1 by time period. That is the time period is the time for one wave, and one mentions that it is one wave. But there are n means many waves, and the time is the time for many waves. So if we just divide, then we will get this much value, or the time for one wave. That is frequency is equal to number of oscillations per unit time. Frequency is equal to number of oscillations per unit time. Similarly, frequency is equal to number of oscillations. Here we consider the oscillation as one oscillation and the time as a time for one oscillation. Use your answer in A1 to reduce the equation relating the speed of the sound to frequency and lambda. So we need to relate speed with frequency and lambda. So we know that V is equal to, since we need to relate this, so initially we don't know that V is equal to f lambda in this form. But we need to show that V is equal to f lambda, or we have to find that V is equal to f lambda. So initially we need to relate this. So now initially we know the equation, that is velocity is equal to distance by time. And since we know and we need to must use our answers from A1. So we know the distance and we know the time. So we know that velocity is equal to distance by time, or velocity or speed is equal to distance by time. So the distance is n lambda, that is n lambda by time, that is n by f. So n and n cancels and f comes above, so it would be n lambda or lambda f. Lambda f, yes, it is lambda f. So distance, that is n lambda by time, that is n by f, and since it is divided, so it comes above. So n and n cancels and the final equation becomes n lambda. So we relate v in terms of f and lambda. Then the wavefront of a sound wave is displayed on the screen of a cathode ray oscilloscope as shown in figure 5.1. So the wave is shown in the cathode ray oscilloscope. The time base is 0.20 millisecond per centimeter. So the time base or the time for one box is 0.20 millisecond. So the time base setting, so yes, the time for one box is given. Determine the frequency of the sound. So we know that frequency is equal to number of oscillations per unit time. So we consider the oscillation of the wave produced as one wave. So frequency is equal to 1 by time period. That is, for one wave, frequency is equal to 1 by time period. So 1 by the time period. So what is the time period? Time period is the time taken for the wave to complete. So 1 box, 2 box, 3, 4. So here we can see that the complete wave is formed in 4 boxes. So the time period would be 0.20, and we have to remember that this is millisecond. So milli is 10 to the power minus 3. 10 to the power minus 3. So 0.20 10 to the power minus 3. And since this time base is for one box, but the total wave is completed for 4 box, so this value into 4. So 1 by time period, we get the frequency as 1250, or approximately 1300, to two significant figures. For part C, two sources S1 and S2 of sound waves are positioned so that as shown in figure 5.2. So this is the source of sound. That is, these two are the source of sound, or the source of sound that produces sound. The sources emit coherent waves. So coherent sound waves. Coherent means that the waves have a constant phase difference. So coherent means constant phase difference between the waves. Coherent means constant phase difference between the waves. So coherent sound waves of wavelength lambda. So we get the value of lambda. A sound detector is moved parallel to the line S1, S2 from position X to position Y. So from position X to position Y, a sound detector is moved that can detect the sound. Alternate positions of maximum loudness L and the minimum loudness Q are detected as illustrated in figure 5.2. So where constitutive interference occurs, loud sound is produced or maximum amplitude is produced, and where destructive interference occurs, quiet sound or minimum amplitude is produced. So here constitutive and destructive interference occurs. Now distance h1x is equal to the distance h2x, distance h2x, distance x2x, distance h2y is 0.70 1.740 meter. So h2y is 0.70 meter as given. So explain what is meant by coherent waves. Coherent waves means that the waves have a constant phase difference between the waves. So the waves must have a constant phase difference between the waves. So state the phase difference between the two waves arriving at the position of minimum loudness Q that is closest to point X. So first of all, what is point X? Now S1 and S2 emit sound, and for position X, so this is the center of S1 and S2. So position X, here we can see that position X is the central maximum amplitude. So position X is the central maximum amplitude, or it is the central position of maximum amplitude. So this is the center between these 2 points, between the 2 sources, or the central maximum amplitude. Now from that is closest to point X, state the phase difference between the two waves arriving at the position of minimum loudness Q. So arriving at the point of minimum loudness Q, so it is mentioned that Q is the minimum loudness, Q is the minimum loudness. So at the position of minimum loudness Q that is closest to point X. So which Q is closest to X? So which value of Q is closest to X? So this value of Q is closest to X. Now we need to find the phase difference between the two positions. So initially at the central maximum amplitude, this is 0 lambda. Then the phase difference would be at the waves arriving at this point is 0 lambda. So this is the, or we can say that this is the path difference. Path difference, and for the phase difference, so the waves arriving at this point has a path difference of 0 lambda and a phase difference of 0. Then for next maximum, that is the next maximum or next loud, it would be path difference of 1 lambda and the phase difference of 360 degree. Then for the other loud or the other maximum, so 1 maximum then 2 maximum, since it is 360 degree, so the other maximum must be 720 degree and the path difference would be lambda. Similar to that, and here constitutive interference occurs. So constitutive interference occurs, and due to this constitutive interference, maximum amplitudes are produced. Now for the destructive interference, so for destructive interference, that is for the quiet sound, so this is for the loud sound, and for quiet sound destructive interference occurs. So destructive interference occurs for quiet sound, and for quiet sound from the central maximum wavelength or central maximum, so from the center, this is the closest quiet sound. So here the path difference from loud to loud is 1 lambda. So from loud to quiet would be lambda by 2. Similar to this, for the next quiet, since loud to loud is 2 lambda, so 1 lambda and lambda by 2. So this would be 3 lambda by 2. That is the path difference. And what is the phase difference? Phase difference would be 180 degree for destructive interference. Since for constitutive interference, we consider the path difference as 360 degree. So this would be 180 degree. And similar to this, for this quiet sound, that is at this position, the quiet sound or the destructive interference occurs. So 360 degree from loud to loud, and then from the next loud to the quiet. So loud to loud is 360 degree, and from this loud to this quiet is 180 degree. So in total, what is the phase difference? So the phase difference in total, we can say that it is 360 plus 180, that is 520 degree, 540 degree. So from the central maximum or central loud to this quiet, that is 360, plus 180, that is 540. Now, what is our question? This question asks us to find from the central maximum, that is x, to the closest q. So what is the closest q? So this is the closest q. And so for this closest q, we know that for q it is distributive interference. So the phase difference, the path difference would be lambda by 2. Since the path difference between loud and loud is lambda, so loud and quiet must be lambda by 2. And what is the phase difference? So for loud and loud, the phase difference is 360 degree. So for loud and quiet, the phase difference would be 180 degree. So what is the phase difference? It is 180 degree for this distributive interference. Since here we can see that distributive interference occurs. So for loud to quiet or maximum to minimum, distributive interference, and from maximum to maximum, constitutive interference. Now, for the next part, determine the distance S1y. So we need to find the distance S1y. So we need to calculate this value of distance. So what would be this distance? Now we need to read the question carefully again. And here we can say that S1x equal to S2x. So that means S2x, that so S2x. So need to relate the lengths to solve the problem. Now the basic thing is that from loudness to loudness, the distance that we get is equal to the loudness to loudness, the distance that we get. Similar to that, from one quiet to the next quiet is one quiet to one loud is the equal distance as one loud to one quiet. This is an obvious thing. Now, distance S1x. So first of all, the information that we have given, the distance S1x. So S1 and x equals to the distance S2x. So S2 and x. So this distance is equal to this distance. Now what is distance S2x? So for distance S2x, now this is the baseline. Here we can see that this is the baseline. So the baseline, so from this loudness to this loudness, this is one distance or one lambda. Similar to this loudness to this loudness, this is also one lambda. So that means here we can see that from the baseline, this length is also equal to this length. So from the baseline or from the right angle triangles, here we can see that this length is equal to this length. That means if this is 7.40, then this would be 7.40. And we know that S2x is equal to S1x. So S1x must also be 7.40. So S1 to x is 7.40 and 7.40, and we need to find S1. So we need to find S1y. So what would be S1y? So we need to find S1y, that is this distance S1y. So S1y would be S1x, that is this distance, plus this distance. So here we can see that we need to find this length. So this length would be equal to S1x, that is 7.40, plus from this point to this point. So this is 2 lambda. That is from one loudness. So from one loudness to the next loudness is 1 lambda. So from first loudness to second loudness is 2 lambda. So here S1y, so S1y is equal to 7.4, that is this distance 7.4 plus 2 lambda, that is 2 lambda. So we get the distance as 9.1 meter. Again, if we just explain, then let me erase this. So basically, we need to find the distance S1y. So S1y, that is S1 from point S1 to point Y. So to find the value of distance, we can first go from S1 to point X, and from S1 to point X, we can go from S1 X to Y. So by covering this distance, here we can see that we covered the distance, that is S1y. So first of all, now here it is given information that S1x is equal to S2x. So S1 to point X is equal to S2 to point X. This length is similar to this length. this is also already given. And here we know that this is the baseline, and from one loudness to one loudness, one loudness to one loudness. So since these two distances are same, so this distance is also same. That means this distance must be same. So since the distance is 7.40 meter, so this is also 7.40 meter, and we know that s2x is equal to s1x. So s1x must also be 7.40 meter. So first of all, we have found that s1x. Now we know the distance s1x, it is 7.40 meter, and what is x to l or y? That is x to point y is 2 lambda. So plus 2 lambda. So the total distance, that is this total distance, is 7.40 plus 2 lambda. So 7.40 plus 2 lambda. And what is the value of lambda? So we have given the wavelength as 0.85 meter. So 0.85 meter, substituting the value, we get the distance as 9.1 to two significant figures. Now for question number 6. A battery of EMF or electromotive force E, that is the electromotive force of the battery, or the total voltage of the battery, that is the EMF of the battery, and internal resistance R. So internal resistance is R, is connected to a variable resistor of resistance R as shown in figure 6.1. So this is the variable resistor, internal resistance. The current in the circuit is I. So initially the current in the circuit is I, and in series circuit we know that the current is same. So the current is I, therefore the current at this point would also be I. That is, the current in series is same, and the potential difference across the variable resistor is V. So for this variable resistor, the potential difference is V, and the EMF we have given that E. Explain in terms of energy why V is less than E. Because we know that EMF, that is E, is divided into V, that is the potential difference of the resistor, plus the voltage across the entire resistance. So EMF is divided into V and the voltage across the entire resistance. And what is the voltage? Voltage is equal to current into resistance. So for internal resistance, the current is I and the internal resistance is smaller. So current is I and the internal resistance is smaller. There is the voltage for the internal resistance. So EMF is divided into internal resistance, voltage of the internal resistance, plus the voltage of the variable resistor. So explain in terms of energy why V is less than E. So why this V is less than E? Because here we can clearly see that voltage EMF is divided into voltage plus the voltage across the internal resistance. So energy is dissipated in the internal resistance. Since energy is dissipated in the internal resistance, therefore the voltage is obviously less than the internal resistance, voltage across the internal resistance. So here, as energy is dissipated in the internal resistance, so obviously this voltage V is less than the EMF. Therefore V is less than the EMF. Now state an equation relating E, I, R and V. So we know that EMF is equal to voltage plus voltage across the internal resistance. EMF is equal to voltage, that is V, plus the voltage across the internal resistance, that is IR, that is I small r. So EMF is equal to voltage plus voltage across the internal resistance I small r. Now the resistance of the variable resistor is varied. The variation with current of voltage as shown in figure 6.2. So voltage against current is shown. Now use figure 6.2 to explain how it may be deduced that the EMF of the battery is 2.8 volt. So how can we deduce that the EMF of the battery is 2.8 volt? So here we have given the variation of, for resistance R, we have given the variation of voltage and the current. So this graph is for only for resistance R, that is capital R. We have given the voltage against current graph for capital resistance R or the variable resistor R. Now explain how it may be deduced that the EMF of the battery is 2.8 volt. Now here we know the equation, that is EMF is equal to I small r plus V. So EMF is equal to I small r plus V, and here we can see that the voltage is in y-axis and the current is in x-axis. So we can convert this equation in terms of y is equal to mx plus c, where m is the gradient and c is the y-intercept. So if we just rearrange and make v in terms of y and I in terms of x, then v is equal to negative IR plus E. So here we can see that v is on the y-axis. So first of all, we have converted this equation in the form of y is equal to mx plus c, where the y-axis is voltage V and the x-axis is current I. There is this I. So if we just further rearrange this equation, then it would be V is equal to I minus R plus E. So V is on the y-axis, current on the x-axis. So y is equal to x, that is current in the x-axis, and the gradient is negative R plus C. C is the E, that is the EMF. So the EMF that we get is C on the y-intercept. So the y-intercept is C. And what is the y-intercept? It is 2.8 volt. So it is clearly 2.8 volt. So the EMF or the y-intercept is 2.8 volt. So by using the equation y is equal to mx plus c, here we can see that the EMF or the y-intercept is 2.8 volt. Now calculate the internal resistance R. So here we know that the gradient is equal to negative of internal resistance. So M is equal to negative internal resistance. So what is the value of gradient? So the gradient is negative of internal resistance. So what is the gradient? So M is equal to, so our initial point is 0, x-axis is 0 and the y-axis is 2.8. So 0 and 2.8, and let's consider another point, that is this point is 1.5, that is the x-axis, and what is the y-axis? It is 0.7. So 0.7. So what is gradient? Gradient is equal to y2, that is 2.8 minus y1, that is 0.7 by x2. So x2, since we consider this as y2, so the x2 would be 0 minus 1.5. So since it is 0 minus 1.5, so the gradient that we get is 2.8 minus 0.7 by negative of 1.5. So the gradient is negative 1.4. So the value of M is negative 1.4. So M is equal to negative 1.4, and we know that M is equal to negative R. So negative R is equal to negative 1.4. So negative and negative cancel, and we get the value of R as 1.4 ohm. So the value of R as 1.4 ohm. So we have calculated the internal resistance. Now the battery stores 9.8 kilojoule of energy. The variable resistor is adjusted so that the V is equal to 2.1 volt. Use figure 6.2 to calculate the resistance R. We need to use figure 6.2 to calculate the resistance R, and this graph is for the variable resistor, that is this variable resistor. Now from figure 6.2, so we have given the energy stored in the battery and we have given the value of voltage, and we need to calculate the resistance. So we know that the resistance is equal to voltage by current. We already know the value of voltage as given. So what is current? So from this graph, for voltage is equal to 2.1. So for voltage, that is 2.1. So voltage, that is 2.1. From the graph, when voltage is equal to 2.1, we need to find the current. So the current is 0.5. So when voltage is 2.1, current is 0.5. So voltage by current, we get the resistance as 4.2 ohm, to significant figure. Now calculate the number of conduction electrons moving through the battery in a time of 1 second. Calculate the number of conduction electrons moving through the battery in a time of 1 second. So we need to find the number of electrons moving through the battery. So again, this is the part of question D part 2. So we need to use figure 6.2. So from figure 6.2, we have found that when voltage is equal to 2.1 volt, the current is 0.5 ampere. So we know that current is equal to charge per unit time. So current is 0.5. So this is not the working at this point. So current is equal to charge by time. So current is 0.5 and charge. So charge per unit time, and we have given the time as 1 second. So we know the value of current and the time. So what is charge? Charge is we need to find the number of electrons. So what would be the number of electrons? So charge is number of electrons, that is number of electrons, and the charge for 1 electron. And the charge for 1 electron is 1.6 into 10 to the power minus 19 coulomb. So the overall charge would be the number of electrons, since basically if we consider this, let's suppose that for 1 electron the charge is 1.6 into 10 to the power minus 19 coulomb, and for n number of electrons, what is the charge, or what is the total charge? The total charge would be 1.6 into 10 to the power minus 19 into n. So for 1 electron the charge is given, that is 1.6 into 10 to the power minus 19 coulomb. So for n number of electrons, what is the charge? So 1.6 into 10 to the power minus 19 into n. And here we need to find the number of electrons or the n. So the total charge that we get is n into 1.6 into 10 to the power minus 19 coulomb. So 1.6 into 10 to the power minus 19 into n, where n is the total number of conduction electrons. So what is the value of n? 0.5 by 1.6. So 1.6 into 10 to the power minus 19. So the value of n that we get is 3.125 into 10 to the power 18. So 3.125 into 10 to the power 18, or approximately 3.1 into 10 to the power 18 to two significant figures, that is 1, 2. So 3.1 into 10 to the power 18. So what we have done in this question is that, so we know that current is equal to charge per unit time, and we know the value of current, that is 0.5, that is 0.5 from the graph. So current is 0.5 and the time is 1 second. So what is the charge? So we know that for 1 electron, the charge is 1.6 into 10 to the power minus 19 coulomb. So we need to now calculate charge, or what is the expression for charge. So for 1 electron, the charge is 1.6 into 10 to the power minus 19 coulomb. So we need to find the number of electrons, number of conduction electrons, or n. So for n number of electrons, what is the charge? So charge is 1.6 into 10 to the power minus 19 coulomb into n. That is the overall charge for n number of electrons. So by substituting the value, we calculate the value of n as 3.1 into 10 to the power 18 to two significant figures. Now, determine the time taken for the energy of the battery to become equal to 1.6 kilojoule. So initially the energy stored in the battery is 9.2 kilojoules. Now we need to find the time for the energy to become 1.6 kilojoule. So what is the difference in energy? That is 9.2 minus 1.6, and this is the difference in energy, or the decreasing energy. So this is a decreasing energy or the change in energy, and we need to find the time for this decreasing energy. So what is the value of time? So for energy, or we can say that power is equal to energy per unit time. So energy is equal to power into time. So we know that power is equal to VI, there is voltage into current into time. So we have given the change in energy, that is the initial energy and the final energy. So we know the value of change in energy, that is if we subtract initial minus final, we get the change in energy, and change in energy is equal to voltage into current into time. So what is the voltage? So since we are considering the battery, so for this battery, the EMF is, or the EMF stored in the battery is, so we have calculated the value of EMF, that is reduce the EMF of the battery as 2.8 volt. So the EMF of the battery is 2.8 volt. That is, from the y-axis we can see that the EMF is 2.8 volt. So for this battery, since we are now considering the battery and not the resistor, so for the battery the voltage or the EMF is 2.8 volt into current. So the current in series is always remains the same. So whether it is a resistor, so the current in series is always remains the same. So whether it is a resistor or a battery or the internal resistance, the current is always I. So the current remains the same, and the current that we get for internal resistance for the resistor R, that is the resistor R, there is 0.5 ampere. So 0.5 ampere is for the resistor R or for the whole battery, because in series the current is same. So the current is 0.5 into time. So after calculating, we get the value of time as 5.4 into 10 to the power 3 seconds. There is approximately two significant figures as the time for the decreasing energy. Also, it is given that the EMF of the battery and the current of the battery remains constant. That means we need to use the EMF, that is 2.8, and the current, that is 0.5. Since these two values are constant, so we need to use these two values to calculate the time for the energy to decrease from 9.2 kilojoules to 1.6 kilojoules by the battery, or for the battery. So this is the time. Number 7 part A. One of the results of alpha particle scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degree. State what may be inferred about the structure of the atom from this result. So we need to determine, we need to state the structure of the atom. So let's suppose for an atom, as the alpha particles pass through, most of the alpha particle remains undeviated, and some of the alpha particles are deflected some of the alpha particles are deflected, and most of the alpha particles are deflected through an angle of 90 degree. So why only small amount of alpha particles are deflected through an angle of 90 degree, or alpha particles are scattered through angles greater than 90 degree or greater than 90 degree? So why small amount of alpha particles are deflected greater than 90 degree? Because for the nucleus, for nucleus, so the nucleus is very small compared to an atom, so and the nucleus is charged. So because as alpha particles are deflected. So first of all, as alpha particles are deflected, and why alpha particles are deflected? Because alpha particles are 4 2, so alpha particles contains 2 protons. So 2 protons, that means alpha particles have a charge of plus 2. Since alpha particles have a charge of plus 2, and nucleus also contains protons plus neutrons, so nucleus is obviously charged, that is positively charged. So since these two positive charges interact, so obviously the alpha particles are deflected, since alpha particle has small charge compared to the nucleus. Therefore, the nucleus is charged and therefore deflection occurs. So now we have stated that deflection occurs. Now why small amount of alpha particles are deflected through 90 degree? Because our nucleus is too small, and so most of the alpha particles pass straight through without any deviation, and only some of the or very little amount of or nucleus is very small compared to the atom. So most of the alpha particles pass straight through without any deviation, and only small amount of alpha particles are deflected through angle greater than 90 degree when they pass close to the nucleus. So when the alpha particles pass close to the nucleus, they are deflected through angle greater than 90 degree, and the rest of the particles pass straight through without any deviation since the nucleus is very small. So the nucleus is very small, therefore only small amount of alpha particles are deflected through angle greater than 90 degree, and the nucleus is charged, therefore deflection occurs. So nucleus is charged, therefore deflection occurs, and since the nucleus is small, so less deflection occurs. For part B, a hadron has an overall charge of plus E or plus E. So the hadron, for the overall charge is plus E. The hadron contains 3 quarks. One quark is a strange quark. State the charge in terms of E of the strange quark. So for up, top, and charm, the charge is plus 2 by 3e. So the for up, top, charm, the charge is plus 2 by 3e, and for down, strange, and bottom, the charge is negative 1 by 3. So for strange, the charge is negative 1 by 3. The other two quarks in the hadron have the same charge as each other. So other two quarks have the same charge. That means if the charge on a quark is x, then the other would also be x, since they have same charge. So by considering the charge, determine a possible type flavor of the other two quarks, explain your answer. So we consider, since the other two quarks have the same charge, so we consider as one charge as q, then the other charge would also be q. So q, since there is 3 quark, so for one charge, one quark, the charge is q, and for the other quark, the charge is q, because they have the same charge. And here we have given that the strange quark, so strange charge has a charge of negative 1 by 3 e. And for the hadron, the overall charge is positive e, or we can say that 1e. So it is positive e. So 2q is equal to positive e, that means 1e. And if we move 1 by 3 to the other side, then it would be plus 1 by 3, 1 by 3e. So what is the overall charge that we get? That is 4 by 3e. That is for 2 quark. And for 1 quark, it is 4 by 3 by 2. That is 2 by 3e. So 2 by 3e for 1 quark. So for 1 quark, the charge is 2 by 3e. So 2 by 3e. So 2 by 3e can be up, top, charm. So it can be up quark or a top quark or a charm quark. So what is the possible flavor of the other two quark? So it can be up quark. That is, you can write just up quark or just top quark or just charm quark. That is, from any of the three, you can write any one value. That is either up quark or top quark or charm quark, as all the three have a charge of plus 2 by 3e. That is plus 2 by 3e plus 2 by 3.